Number 78 says the radius of a circle is increasing at a constant rate of 2.2 meters per second. The radius is changing over time. It's increasing, so it's positive, and it's a positive 0.2 meters per second if you desire to write in the units. It says, what is the increase in the area of the circle at the instant the circumference is 20 pi meters? Well, the area for a circle is pi r squared. The area changing over a function of time, dA dt, would equal 2 pi r dr dt. It seems to me that we have the dr dt. What we need is the radius. We know the circumference of a circle is equal to 2 pi r. They tell us that we want to know how this area is changing the instant the circumference is 20 pi. Well, if we put 20 pi in for c, it seems that we can solve for the radius. 10 equals the radius. So 10 is the radius. dr dt is a positive 0.2. So dA dt is equal to 2 pi times 10 times 0.2. Well, 0.2 of 10 is a 2, and 2 pi times 2 is equal to 4 pi. And so I come looking for the answer, and it seems to me that it's 4 pi square meters per second. Number 78. Number 79 is asking the question, when does the limit exist as x approaches 4? Recall that the sided limits have to equal if the limit is to exist. So on this Roman numeral 1, as we approach 4 from the left, we're definitely going at what is the target is where the hole is, and if we come at 4 from the right, it seems to me we're going to the same place, and so this one actually exists for sure, right? We've got the same sort of thing happening with Roman numeral 2 here. If we come at it from the left, we're going to the same target as we get when we come from the right. The fact that it doesn't exist at 4, if it's something else like in Roman numeral 1, or it doesn't exist at all in Roman numeral 2, doesn't really matter. All that matters is that the target is there. And it's definitely there, and it's the same coming from both directions. Roman numeral 3, I hope you can see the problem. The target is one thing when we come from the left, and it's a different thing when we come from the right. There is no limit for the last one, right? And so to summarize this one, or to get it down here, it seems that D is our only choice. That's number 79. Number 80 is talking about a continuous function. And remember, if it's continuous, that implies that the limit at any point is equal to the value at that point. I don't know that that's important here. It's continuous in the interval. It's differentiable in the interval. It's not differentiable at the endpoints. Not surprising, but it's continuous at the endpoints. It says f of negative 2 is negative 5. F of negative 2 is negative 5. We have a point at negative 2, 5. It says here that f of 1 is 4. So we have a point at 1, 4. And it says which of the following could be false. Now remember, between those two endpoints, it's continuous and differentiable. So the first thing says there's a number c between these two endpoints such that f of c is 0. F of c is 0. In other words, it must cross the x-axis. And if it's continuous, right, that has to be so. You know, I could draw it on here real quick and then remove it, but you get the idea. If it's continuous, somewhere it has to cross the x-axis. So this is true. It's true by the intermediate value theorem, which says in so many words that in a closed interval it has to take on every value between, you know, from the left to the right. So that's a true statement. B says there exists a c between negative 2 and 1 such that the derivative equals 0. Well, that could be true, but we could have a simple line segment between these two endpoints that would be differentiable everywhere, would be continuous, and would not have a local max or min. So it seems to me right away that B could be false. This could be false. It could happen, like we could have something like a parabola whose vertex is between negative 2 and 1, and that would clearly, you know, meet that requirement, but it doesn't have to be anything like that. Letter C says there's a c between negative 2 and 1 such that f of c equals 3. Well, somewhere in there, to get from negative 5, excuse me, I've been having that labeled wrong all this time, from negative 5 up to 4, somewhere it's got to be 3. Again, that's the IVT, and that must be true. And we're just going through these to talk about what's at hand here. It says there exists a c somewhere between negative 2 and 1 such that the slope or direction or derivative equals 3. Well, if you take a look at what I've got drawn here, it seems to me that this change in x, this delta x, is equal to 3, and this change here, this vertical distance, this change in y is 9 units, and 9 over 3 equals 3. So somewhere in there, if it's a line, it's got to have a slope of 3. And if it's in fact any kind of curve, somewhere it'll pick up 3 as a derivative. That's the mean value theorem, and that must be true. And finally, there exists a c in the closed interval such that f of c is greater than x, f of x, for all x, could be equal to for all x on the closed interval. Well, that's the extreme value theorem. This is the EVT, and that must be true. There has to be a max, and there has to be a min on a closed interval. So B is the answer for number 80. A long explanation. Number 4, I cheated a little bit. I went and used the calculator ahead of time. It says let f be a function with a derivative given by, and it says how many relative extreme does f have on the interval 2 to 4. So I took my calculator and I restricted the window from 2 to 4. You know, I went over and I took the zoom window and I took and changed the start and the stop for my window. And you know, this is a graph of the derivative, right? This is f prime. Kind of mislabeled here. This is f prime x, right? That's what we're looking at. And it seems to me that the derivative changes from negative to positive, back from positive to negative, from negative to positive, and finally from positive to negative. You know, when you go from a negative to a positive, that's a minimum. And this over here, from positive to negative, must be a max, a min, and a max, right? We don't know if these are absolute or not, but they certainly are those extrema, relative extrema. 1, 2, 3, 4 of them, right? So pretty clear from the picture that there are exactly 4. And let's see, one more in this group. And again, I did a little work on the calculator ahead of time. It says the rate of change of altitude for a hot air balloon is given by this function. Sometimes up, sometimes down. It's going between 0 and 8. And it says which of the following expressions gives the change in altitude for the balloon during the time the altitude is decreasing. So if it's decreasing, it means its derivative or rate is negative. We've got this rate function, right? And maybe you don't like the fact that the calculator labeled it that way, but that's the rate function there. And I just put it in X to keep the calculator happy. Anyway, I see that it's negative, right, between these two moments. And so I took the calculator and I said, how about analyzing the graph and finding me the zeros? And the calculator was very good about that and found me that those were the 2 locations. And I said, you know, what I want to do is if I want the total change in altitude, the change in altitude, I want to take and accumulate all the negative or decreasing values. How far did it go down between between 1.572 and 3.514? And this function is t cubed minus 4t squared plus 6. In other words, this area is that accumulates the amount of decrease. And so if you look to the list there, I believe that it has to be letter A, right? And that would be correct. That's it for this group. And we'll go on to the next one in a moment.